I'm telling you, Becky the body at... Oh, you're there! I'm currently being held at gunpoint. And this is my master's thesis in engineering physics at IST, entitled The Soft-Hard Antenna Spectrum in the Presence of a QGP. The theory that best describes the fundamental building blocks of matter so far is the standard model of particle physics, which includes a bunch of different particles. However, for this work, all we really care about are the quarks and gluons, collectively referred to as partons. Besides the electrical charge, which you are probably aware of by now, partons also carry color charge. Why color, you might ask? Well, that's because physicists hate clarity. And, as an added bonus, it allows us to name the physics that governs this sector quantum chromodynamics, which sounds really complicated. Because it is. But if these particles are so fundamental, why have you never heard of them before? That's because of one of QCD's main features, confinement, which states that at low temperatures, quarks, much like teen singers in the 90s, always come in groups. These groups are overall neutral in color and can be divided into mesons, such as pions or kaons, or baryons, such as neutrons or protons. On the other hand, it was predicted back in the 70s and 80s that at extremely high temperatures, like 2 trillion Kelvin, a new state of matter would show up, where not only would this confinement be lifted, but some other symmetries would be restored. This state of matter is hypothesized to have permeated the entire universe shortly after the Big Bang, and thus was appropriately named the soup. I'm joking, it was named the quark-gluon plasma, but wouldn't it be much cooler if it was just called the soup? And in the year 2000, the QGP was observed at CERN through the extremely scientific practice of smashing stuff really hard. Small problem, it has a very short lifetime, of the order of just a few femtoseconds. Those are quadrillions of a second. So how do you study something that happens so quickly? Well, we use indirect methods, such as probes that are affected by that medium. This way, we can take a close look at the properties of the QGP by examining the imprints it left on those probes. The most studied of these probes are jets, reconstructed parton showers with an approximate cone shape that lose energy while traversing the QGP. We say that the jets are quenched by the medium. Therefore, we need mathematical tools that describe partons in the medium, accounting for both energy losses and shower radiation to accurately describe jet quenching. Recently, this approach has been extended not only to individual particles, but also to quark-anti-quark pairs, referred to as antennas, and whose behaviors is much different than the mere sum of the parts. This is where my work comes in. The aim is deepening our understanding of jet quenching by extending some calculations done in the previous decade. With the supervision of Guilherme Miano and Liliana Apolinário, I will leave some approximations regarding the energies of the constituents of the antenna, allowing them to be vastly different, resulting in a more general spectra of gluon emission. So now, if you'll excuse me, I'm going to probably get shot in the head because of Becky!